Morning, everyone. We'll get started. Hopefully the test went well. You had until last night at midnight to complete it. I think I think there may have been one person who didn't take it. Looks like the majority of you all took it, which is great. Okay. So we had started talking chapter 5 stuff, molecules and compounds. And we left off looking at polyatomic ions. So when we have some sort of like multiplier or something within parentheses. So let's say I'm going to give you guys another one to look at. Ca3PO4 2. This is something called calcium phosphate. And don't worry about the name just yet. We'll get into that a little later, but I think some people were asking, oh, what are these named? So tell me how many you have of each element within this compound. Okay, so there's 3 different elements. We've got calcium, phosphorus, and oxygen. The number of calciums, pretty easy. There's a calcium and there's the 3 that's associated with it. So we just have 3 calciums. Phosphorus, there's 1 phosphorus within the parentheses, but there are 2 of these packets. You want to think of these polyatomic ions as like little packets. So we have to have 2 of them. So we need to take the 2 times the 1. So 1 within times 2 for an overall 2. Oxygen, there's 4 within, and we have 2 of the packets for a total of 8. So that's how you're going to be reading things with like parentheses and stuff like that. Always multiply the outer guy by the inner guy, multiply. So when talking about types of chemical formulas, so that last chemical formula that we looked at, and a lot of the chemical formulas that we look at for general chemistry, because we're doing inorganic chemistry, are what are called empirical formulas. And empirical formulas give the relative number of atoms for each element in a compound. When I say relative number, I mean the like lowest whole number ratio. On the other hand, a molecular formula will give you what is actually happening in real time. So a molecular formula is always going to be some sort of multiplier of the empirical formula. The molecular formula is what's happening in reality. The empirical formula is just the lowest ratio. Now, sometimes the molecular and the empirical formula are the same. Okay, like for instance, table salt, NaCl. Its empirical formula is NaCl and 1:1. Its molecular formula is NaCl 1:1. An example where we have a difference in these two is hydrogen peroxide. So hydrogen peroxide in real time, if you were to go out and like look at the molecule, it would be 2 hydrogens for every 2 oxygen, H2O2. But its empirical formula, or it's sort of like shorthand formula, would just be a ratio of HO. 1 H for every 1 O. But the real molecule is really 2 H's for every 2 O. So how these two things relate to each other is, you know, the molecular formula, you would divide it by some sort of whole number to get the empirical formula, or the empirical formula, you would multiply it by some sort of whole number value to get to the molecular. For a lot of compounds, like I said earlier, such as H2O, the molecular formula and the empirical formula are the same. In real life, it's H2O. The lowest ratio is also H2O. A structural formula is a formula that represents a formula using bonds and shows how the atoms in the molecule are connected to each other. So this, we'll kind of get into this a little bit later on in another chapter. Here are some of the types of like visual structures here. So we've got this one, like if we've got, for instance, the molecular formula methane, CH4. We can draw it like this in two-dimensional space with a carbon and 4 hydrogens, or we can like stretch it out into this ball and stick model, or we've got these space filling models. These two things will come into play in not the next chapter, but the following chapter. All right, so the macroscopic world, what we see is affected by the microscopic world. The formula that we have here will determine what we see and the behaviors on a macroscopic level. So we had, when we talked about last chapter, pure substances can be either an element or a compound. We actually want to break that down a little bit farther. So we're going to say that an element can be either atomic or it can be molecular. And then a compound, we're going to break into being either molecular or ionic. We'll explain all these in a moment. So we've got our atomic for elements, we've got our molecular, and then for compounds, we also have molecular and ionic. Sometimes this is called covalent too, because they have a covalent bond or they're sharing electrons. So let's look at the difference between these two things. So atomic elements are those that exist in nature with just single atoms as the base unit. Most of the elements on the periodic chart fall into this. So aluminum is just a series of aluminum atoms as their base unit. A molecular element, on the other hand, which is sometimes called a diatomic molecule, they don't normally exist in nature as single atoms as their base unit. Instead, they form what's known as a diatomic molecule, where two of them will bond to each other, and that will be the base unit. So an example of this is oxygen. Oxygen doesn't just exist as a free element like this. It will actually bond to itself, so we get O2. Here we've got a bunch of mercury. The mercury, it's just a series of mercury atoms lined up. Over here, we've got a molecular or a diatomic chlorine. If we were to look at this pure chlorine gas on a microscopic level, we would see that the chlorines have clumped together. Okay, so Cl2 is the base unit. These are all the things that form diatomic molecules. You do need to know these. So if you look at your periodic chart, we've got hydrogen. We jump over, so go hydrogen, move to the right, jump over to nitrogen. And then you go nitrogen, oxygen, fluorine, and then drop down chlorine, bromine, iodine. So you make like an upside down L. But don't forget hydrogen. Another way that I've heard someone say, remember this, have no fear of ice cold beer, but you have to remember that cold is chlorine, not carbon. Okay? So I think visually it's just easier to know, go hydrogen, jump over to nitrogen, make that upside down L to iodine. If it's not one of those, it's not a diatomic. Now, one thing that people get confused about with this is that they think, okay, so for instance, nitrogen. Well, if nitrogen is N2, that means that anytime it's bonded to something else, it also has to be N with a 2. That is not the case, okay? Or oxygen has to be O2. That's not the case. If we have oxygen as a free element by itself, free element, it is going to be O2. But let's say oxygen is bonded to something like magnesium. The formula for magnesium oxide is MgO. There is no 2 here. I will tell you in a couple minutes why there is no 2 here, but for now, you're just going to believe me, there's no 2 here. This gets people confused. They're like, well, isn't oxygen a diatomic? It's a diatomic when it's by itself. When it's bonded to something else, it doesn't follow that rule, okay? It doesn't have to be a 2. Could be a 1, could be a 3. So just make sure you differentiate that. You don't use this diatomic thing all over the place. You only use it as a free element. Okay, so the next thing, the element part is pretty easy, right? It's either a diatomic or not. The compounds, this is where it gets tricky. If there was one chapter that I could say, this is the most important chapter of the semester, know how to do this, it would be this chapter right here and now. All right, chapter 5, this is all in naming and nomenclature. This consumes so much of, I think the final, like there's like 50 questions and like 10 of them are related to naming. And then later on, that's like 20%, you know, and then later on, when we're doing more complicated things, this naming stuff comes back. Okay, so you want to be able to do this. So first thing when it comes to doing anything with naming a compound is you have to be able to tell me if it's a molecular or an ionic compound. Molecular compounds are formed when it's 2 or more nonmetals. The base unit of a molecular compound is a molecule. So it forms a little molecular packet. And then the greater mass of it is little molecules stuffed together. An ionic compound contains 1 or more cations paired with 1 or more anions. So that means usually we have a metal combined with some sort of nonmetal. That's it. That's how you differentiate them. A molecular will be all nonmetals. An ionic will have a metal in it. If you can't differentiate those two, the process of naming is going to get thrown out the window because you're not going to know how to, like the way we name these things is different than the way we name these things. So if that can't be separated, it's really hard to name properly. So let's just do a couple. I want you to tell me whether it's molecular or it's ionic. I'm just going to write some compounds out. Okay, you will need a periodic chart for this whole chapter. So if you don't have one sitting right next to you, have one. Okay, so all I want you to do right now is let me know, is it molecular or is it ionic? I'll give you a couple more over here. I'll give you a minute and a half for that. Okay. So we want to be looking at what is in it to determine what it is. This first thing here, Na, this is a metal. Metal. If the first thing you bump into is a metal, you can go with ionic. Usually if the first thing you bump into is a non-metal, it's going to be molecular. Right here, I've got a non-metal nitrogen and a non-metal oxygen. So this we're going to go with molecular. Sulfur and oxygen are both non-metals. So we're going to go with molecular. This thing down here, a little more complicated looking, but it still follows the same rule. What's that first thing we bump into? Magnesium, which is a metal. So this is ionic. Over here, Fe, that's a metal. It's a transition metal that has an unpredictable charge, but it's still a metal. So we're going to go with ionic. This next one here, H2O, water, non-metal and non-metal, molecular. CO, carbon monoxide, both non-metals, molecular. Okay. Any questions on that? Any questions on how you decide what's a metal? Remember when looking at your periodic chart, I said find the zigzag line, okay? If it's to the left and down from the zigzag line, it's a metal. If it's to the right and up of the zigzag line, it's a non-metal. So why is it so important to differentiate these? Well, when I'm naming things that are ionic or when I'm trying to write formulas for things that are ionic, it's going to be totally different than what we do for molecular. I think the ionic is a little bit harder, and we start with that. So let's go through that. One of the differentials between these two, and I sort of already touched on this though, but the base unit in a molecular thing is an actual little packet or a little molecule of whatever that formula is. So if it's CO2, you're going to have a bunch of these cute little CO2 molecules. That's not the case for ionic. Most of the time for ionic units, you get like for instance, the formula NaCl. This is what's called a formula unit. It means that it's the lowest ratio within like a three-dimensional matrix. So it's actually forming a much more structured base unit. So we'll have an Na and a Cl, and it'll be attached to an Na and a Cl next to it, above it, forward, back. That's not the case with the molecules. The molecules aren't like kind of affecting each other as they are here, where you get this nice structure. So when looking at it on a macroscopic level, things like table salt will have a really uniform structure. It forms those really nice, neat crystals. Versus dry ice, which is just cold CO2, it has a much more haphazard look because the molecules aren't forming that three-dimensional lattice. Okay, so ionic compounds. When a metal, which likes to lose electrons, combines with a non-metal, which likes to gain electrons, remember metals are cations, non-metals are anions. One or more electrons will go ahead and transfer from the metal to the non-metal. And what this does is it creates a positive ion and a negative ion. And what do positive and negative things do? They attract each other, so they will stick together. So the electrons are moving from one thing to the other, they're self-ionizing themselves, and then they're sticking together. A compound composed of a metal and a non-metal is ionic. The base unit of an ionic compound is its formula unit, and unlike molecular compounds, ionic compounds do not contain individual molecules. Okay, so we're getting this three-dimensional alternating array of whatever the formula unit is. So writing formulas for ionic compounds. First thing we want to do is review the charges on the ions. So predictable charges, remember if you're in column 1, outside of hydrogen, really. So lithium, sodium, potassium, rubidium. I told you guys to put a +1 above that. Column 2, +2, Column 3, really just aluminum and gallium, not including boron, we put a +3. Jump over to the nitrogen column, nitrogen and phosphorus, we put a -3. Oxygen, sulfur, we put a -2. Fluorine, chlorine, bromine, iodine, we put a -1. And then above the helium, neon, argon, krypton, we put a 0 with a strike through it because those guys don't form charges. A couple other predictable charges. So go to aluminum on your periodic chart, that's a 3+. Go down into the left, zinc is going to be a 2+. Go down into the left, silver is going to be a 1+. So those guys always form those charges. They're not going to vary from that. That makes it a little easier to write their formulas. Ionic compounds will always contain one positive and a negative. Okay, so the positive and the negative are going to then, working into this third point, the positive and the negatives need to balance each other out, or the sum of the positive charge from the cation must equal the sum of the negative charge on the anion so that the overall molecule is charge neutral. So when I write NaCl, this guy right here, I don't put a charge in the upper right-hand corner because this whole thing is charge neutral. What is the charge on sodium? Na, it usually likes to form a plus charge, right? What's the charge on chlorine? A minus charge. Those two things, when they come together, when we combine them into NaCl, the positive and the negative will balance each other out to give us an overall neutral charge. So when writing a chemical formula for an ionic compound, there's a series of steps that you can follow. It says, first, write the symbol of the metal and its charge, followed by the symbol of the nonmetal and its charge. Make the magnitude of the charge. Magnitude means the numerical value, not the positive or negative. That doesn't matter. Just make the size of the charge on each ion without its sign become the subscript of the other ion. If possible, reduce subscripts to reduce any, to give a ratio that's its smallest whole number, and check and make sure that the charges cancel. So this is the fastest way to come to a charge neutral molecule. We can look here, aluminum and oxygen. What is the formula for aluminum and oxygen? There's only one possibility for that formula. It's going to be Al2O3. Where is that coming from? The 3 on the magnitude of the aluminum gets flipped-flopped to the subscript of the oxygen. Okay. The 2 on the oxygen, just the magnitude, not the charge, gets put down as the subscript of the aluminum. That is just the fastest way to get a charge neutral molecule. You could think in your head, okay, well, aluminum has a 3+ and oxygen has a 2+. So I know that I'm going to need to like have a total of a 6+ charge and a 6- charge, which would then give this a 2 and this a 3. The fastest way is just to flip flop. We can go back and check and make sure that it's charge neutral. So there's no charge written in the upper right-hand corner, but let's just make sure. So aluminum, we know has a 3+ charge. And how many of them are there? There's 2 of them. So I'm going to multiply it by 2 for a total of 6+. The oxygen has a 2- charge, and there's 3 of them for an overall 6- charge. When I add those together, it equals 0. Okay, neutral charge. Fastest way to do it. This one, they need to go a step further and divide it by a factor of 2. So this would become MgO. Anytime we're dealing with ionics, you always want the lowest ratio. I don't know why they didn't reduce it on the slide, but they didn't. So let's practice some of those. We'll do one together, and then I'm going to give you a couple to do on your own. I want you to combine, or let's combine calcium and sulfur. So if I'm going to combine these two things, I'm going to write the charge. I'm going to write the symbol with its charge. Calcium is in the second column, so it always forms a 2+ charge. Sulfur is in the fifth column, or rather sixth column. This always forms a 2- charge. So flip-flop, calcium will get the 2, sulfur will get the 2 from the calcium, and then we reduce down, divide by 2 to get CaS. So let me give you a few. I'm not going to write the formal names. I'm just going to write the two things I want you to mix together or bond together. So let's do potassium and phosphorus. Aluminum and sulfur. Strontium and chlorine. Okay, I'll give you 3 minutes for that. Okay, so looking at this, potassium and phosphorus. Potassium is not P, it's K, and it has a plus charge. Phosphorus is the P, and it has a 3- charge. Does anyone have any questions where I'm getting those charges from? I'm not just pulling them out of thin air. Okay. All right, so we're gonna flip-flop. The 3 comes down to the K, the 1 comes down to the P. So we should end up with K3P. Aluminum and sulfur, aluminum, Al with a 3+, sulfur always has a 2-, flip-flop, Al2, S3. Strontium and chlorine, strontium, Sr, always has a 2+ charge. Chlorine always has a minus charge, flip-flop. We should get, pen keeps getting in my way, SrCl2. Any questions with that? Okay, because we're gonna layer some more stuff on here. So we're gonna go back to that idea of polyatomic ions. Writing formulas for compounds that contain a polyatomic ion. So here is a list of polyatomic ions. Normally, I would have you memorize about 10 of these, but since we are in an online format, you guys will be able to just reference a polyatomic ion sheet. Anytime you're working on one of these naming things and it's like not following the system or you're having trouble figuring it out, it's probably a polyatomic ion. That's the problem. So some of the polyatomic ions that we see quite often are here on this list. Are there more than this? Yes, there's definitely more polyatomic ions than this. How to read a polyatomic ion. So let's look at carbonate, this thing right here. CO3 2-. I want you to make sure that you're separating out subscripts from superscripts. So we can even draw like a line here. The subscripts are the things below this midline. Those are talking about atoms. The superscripts are talking about charge. Okay, so don't mix those up. So when looking at carbonate, I'm just going to write it on a different over here. If we're dealing with carbonate, it is always CO3 with a 2- charge. This tells me that I have 1 carbon, I have 3 oxygens, and this whole thing combined together has a 2- charge. So if you want, you can even start getting in the habit of sort of circling where the atoms are and leaving the charge hanging on the outside of it, so you know that the charge is talking about that whole packet. All right, the 2- isn't talking just about the oxygen. Sometimes that throws students off. They think, oh, it's just the oxygen that has the 2- charge. No, the whole packet, that whole unit has that charge. Remember what this thing is. It's a polyatomic ion. Okay, multiple atoms that have an ion or a charge to it. So I'm going to give you another polyatomic ion. I want you to tell me how many atoms are in it and what is its charge. This thing is called sulfate. SO4. All right. So tell me how many of each atom you have and what its charge is. Just 20 seconds or so. Okay. I'm going to circle where the atoms are, just so that we have an idea together what we're looking at. This part talks about how many of each we have. Sulfur, 1. Oxygen, 4. Charge, that's outside. Charge for this guy is a 2- charge. Most of the polyatomic ions you guys are going to work with are negative charge. So they're going to take the place of the nonmetal. There is one polyatomic ion that has a positive charge that sometimes takes the place of the metal. That's ammonium. You see ammonium down here, how it's NH4 with a plus charge? That can be easily swapped out for the metal. Okay, what is going on here? It's not giving us any practice with that. So we're gonna practice with polyatomic ions now, since we just talked about them. It looks like it doesn't bring it up for a little while. So just like you have, a metal with a positive charge and a non-metal with a negative charge, and you flip-flop charges to get it charge neutral, you do the exact same thing if there's a polyatomic ion. All right. It seems a little more intimidating because it's more atoms, but it's the same process. So let's combine, let's take sulfate here. We're going to combine it with, let's just do sodium. Okay. So we've got sodium and we're going to add it to sulfate. Sodium is Na with a plus charge. Sulfate is SO4 with a 2- charge. Start getting in the habit, anytime you see things ending in ATE or ITE, that those are polyatomic ions. You're going to want to reference your polyatomic ion chart for that. How do you know that sulfate is SO4 2-? You're going to have an appendix, or you're going to have them written down in your notes somewhere so that you can reference that. So when I'm doing this, I kind of like to circle the atoms so that I don't confuse them with the charge. Treat that as a packet. Don't break it up. Just like you treat Na, the N and the A as a unit, you're not going to break that up. We're not going to break this up. All right. All we're going to do is flip-flop charges. So the 2 is going to drop down to the sodium. The 1 is going to drop down to the sulfate. So I should have 2 sodiums, Na with a 2, and 1 sulfate, SO4. There's a 1 here. Do I need to put it in parentheses and say that there's a 1? No, I don't need to do that. Okay, I can, if I'm writing it, it means I have 1. Let's do sulfate with one that's, sorry. Let's do one with sulfate that requires us to use some parentheses. So let's say we have, we'll do aluminum and sulfate. Hold on 1 second. So we have aluminum and sulfate. Let's write the symbol for aluminum, Al, and it always has a 3+ charge. Sulfate is SO4, and it has a 2- charge. That hasn't changed. I'm going to circle my polyatomic ion, at least the atom part of it, and keep the charge on the outside. So when I flip-flop here, the 2 is going to come down to the aluminum. So this is going to be Al with a 2. The sulfate, how many sulfates do I want? Or do I need? I need 3 of them. So in order to tell the reader you have 3 of them, we're going to put this thing in parentheses. And we're going to put a 3 on the outside of the parenthesis. So it becomes Al2, SO4, 3. And the SO4 is in parentheses to denote that you've got 3 of them. That's why I preface, maybe circling this thing so that you know that it's a unit. So that 3 has to apply to that whole thing, not just the oxygen, not just the sulfur. You don't want to swap the 4 out for the 3, nothing like that. You want to treat it as a packet. I'm going to write in red some of the things that I see students do that are incorrect. Okay, so don't do these things. But one thing I'll see students do is instead of flip-flopping, they'll just drop the number down. So they'll say, oh, aluminum is a 3, so that means I have 3 aluminum. So they'll go Al3, and the sulfate, I have 2 of those. Okay, that is not charge neutral. This 3 does not go here, the 3 goes here. This 2 does not go here, the 2 goes here. We can double check it, and I can prove to you that it's wrong. Aluminum has a 3+ charge, and there are how many in this formula? There's 3 of them. That's a 9+ charge. Sulfate has a 2- charge. How many of there are? How many of them are there? There are 2 of them for an overall 4- charge. Does that neutralize out? It doesn't. It's not charge neutral. Doesn't equal 0. Okay, so we don't like that. This one we like. This guy's good. This is a 6+ and a 6-. Okay, another thing that I see students do, they don't put this as a packet. So let me scroll down here. Again, these are things I don't want you doing. But sometimes I think it's good to see what is wrong to know what's right. So I'll get people, okay, I'm gonna flip-flop this thing. And they'll go, aluminum, there's 2 aluminums. And I've got 3 of these sulfate things, whatever. So SO3, and I'm done. Okay, what has happened here? They've taken what was 4 oxygens and they've taken the 3 and replaced it. And now we have Al2SO3. This is not the same thing as this. Remember when I told you guys don't change subscripts? Subscripts are the defining quality of the material. If it's sulfate, it better be SO4. SO3 is another polyatomic ion that's called sulfite. It has totally different properties than sulfate. We do not want to do that, okay? We don't like that. Another thing I see students do, go Al, we've got, it's a 3+, SO4 with a 2-. And they'll say, okay, I'm going to flip-flop this thing, and I'll go Al2, SO4, 3. And they'll just leave the parentheses off. We definitely don't have 43 oxygens. That would be a very odd molecule. So we want to make sure we're putting those parentheses in. Before I give you guys 4 or 5 of these to practice, any questions on this system of flip-flopping or this system of flip-flopping with a polyatomic ion? You got to let me know. If you did one of these mistakes here, no worries. Hopefully we cleared up why we don't want to do those. Okay, I'm going to give you a few to play around with. You need to have a polyatomic ion sheet to do these. If you don't have one, you have a cell phone, I'm assuming. Go ahead and, I got one question here. Where do the charges come from again? Okay, Chrissy, the charges come from, because I told you them. So everything above column 1 has a +1 charge. Everything above column 2 has a +2 charge. Yeah, so I just had you write those on the periodic chart. We can look here. Where are you? Predictable charges. I know that there's a slide somewhere with it. Okay, so these are all +1. These are all +2. This one is a predictable +3. 3, 2, 1. This is 3-, 2-, 1-. As far as the polyatomic ions are concerned, those are just the charges that go with that polyatomic ion. That is the way that it forms. So carbonate is always going to be CO3. Pull up the carbonate is always going to be CO3 2 minus. That is the definition of carbonate. I think the biggest thing I see students do is that they'll, I mean, and again, it's not as important because you guys get to have a reference, but what I'll see is students will memorize, oh, that carbonate is CO3, and they totally forget the charge. The charge is just as important as how many atoms you have. Okay, so don't leave off the charge. Does that help at all? Okay, cool. So let's do some of these. I want you to combine calcium with nitrate. If you don't have a polyatomic ion sheet, use your cell phone, just type in polyatomic ions and it'll pull these up. I want you to combine cesium and phosphate. I want you to combine aluminum and carbonate. And let's see, silver and nitrite. Oh, and I'll give you one more just to kind of mess with you guys. Let's do iron. I just gave you the formula. Iron and sulfate. Don't stress too much about this one. Give it a hot second, and if you can't figure it out, it's totally fine. Okay. I'll give you all, give you 5 minutes for this. All right, bring you back. Look at these. So we've got calcium and nitrate. Calcium is a metal with a predictable charge of 2+. Nitrate is a polyatomic ion, NO3, with a -1 charge. I'm going to circle this without the charge because I want to keep that as a unit. Flip-flop. I should have 1 calcium for every 2 nitrates. So I'm going to put the nitrate in parentheses, NO3, and I'm going to put the 2 on the outside of the parentheses. Cesium and phosphate. So cesium is, CS, and this is a +1 charge. Phosphate is PO4 with a 3- charge. Flip-flop these things. I should have 3 cesiums, CS3, for every 1 phosphate, PO4. If I only have 1 phosphate, I don't have to put it in parentheses, okay? Aluminum carbonate. Aluminum is Al with a 3+ charge. Carbonate is CO3 with a 2- charge. We're going to flip-flop. Aluminum gets the 2-, or the 2 rather, so Al2. Carbonate gets the 3. CO3 parentheses 3. This kind of throws people off when they see the 3 and the 3 together. They're like, 3 and 3, oh, can you have that? You can totally have that, yeah. Silver nitrite. All right, silver is Ag+. Nitrite is NO2-. NO3- is nitrate. It is important to note, are you looking at an ending of an ATE or an ITE? I'll tell you guys in a little bit how you can Turkey, stop. Sorry, I have a French bulldog named Turkey and he is in here with us today. So I'll tell you guys how you can differentiate the 8s and the ites. So we flip-flop and we get AgNO2. This one here, you can't do it. That's the trick. You can't do it currently. Why? Okay, iron, Fe. What is its charge? I don't know. It's in the transition metal area. It can have varying charges. So what is its charge? We don't know. So the way that this is written there isn't enough information. I would have to write something like this, iron with a Roman numeral 3 to let you know that we're dealing with iron with a 3+ charge or something. I didn't write anything there, so you can't do it because sulfate is SO4 with a 2-. How do you flip-flop if you don't know the charge? You can't. I will show you how to work these transition metals more a little later. For now, we don't have the knowledge to do that, okay? But you should, at this point now, be able to name any metal and non-metal and any metal and polyatomic ion, as long as you have an appendix. Is that making a little bit more sense why certain things are combined the way that they're combined? You will never have cesium and phosphate come together in any other way but this. That is its magic combination to give it the lowest ratio and have a neutral charge. Does it get more complicated than this? Of course it does, especially when we get into those transition metals. So you guys can write the formulas now. We're going to talk about naming, which is sometimes it's called nomenclature. Nomenclature is just a fancier way of saying naming. So chemists have developed a very systematic way to name compounds because there are so many compounds. Trying to learn every compound's everyday name would be insanity, right? Like for instance, down here, we've got H2O. The common name for this is water. The systematic name is dihydrogen monoxide. Now for water, we just know that that's water because it's like everywhere. But for other compounds, to know its like everyday name would just drive you crazy. There's so many thousands and thousands and thousands of compounds. They actually did something really funny. It was on one of those like YouTube channels where they went around with like a placard, and they told people, do you know, sign this petition. Do you know that they're putting dihydrogen monoxide in your water? And people were all up in arms about it. Oh yeah, I'll sign this. How could they put dihydrogen monoxide in our water? Well, dihydrogen monoxide is water. So if you ever happen to be on the street and somebody comes up with a camera and is telling you that, don't fall for it. So anyway, back to losing my train of thought here. So we've got this systematic way of naming things. The first thing when it comes to naming is just determining, is it ionic or is it molecular? Because the way we name metal nonmetals, ionic stuff, is going to be different than the way that we name nonmetals. Common names can only be learned through familiarity. There is no system. Systematic names can be learned. If you know the system, you can name any compound, and I'm going to teach you the system. So the first thing to your system, I kind of want to hop ahead because there's a really nice flow chart at the end of these slides. This thing right here. So this is kind of the way that you want to move through naming. You want to determine, is it ionic? Is it molecular? Or is it an acid? This has its own way of naming versus this. So ionic or molecular. So we're going to talk about ionic first. If you've decided, I'm pretty sure that this is ionic. It's made of a metal combined with some sort of non-metal, or it's a metal with a polyatomic ion. Then you need to go one step further. You need to determine, is it a metal that forms only one type of ion? This is sometimes called a type 1. Or is it a metal that forms more than one type of ion, or a type 2? What are some examples of metals that form only one type of ion? Anything in column 1, sodium, potassium, anything in column 2, calcium, magnesium, aluminum. What did we say are transitions? Zinc and silver. Those also form, all of those, including some of the other ones, form predictable charges, just one type of ion. What if it forms more than one type of ion? If it forms more than one type of ion, we have to do extra work. These are things like titanium, chromium, cobalt, all the transition metals, platinum. All these things do more varying stuff, so we have to add information. Let's start with the easier one though, the metal that forms only one type of ion. Call those type 1, transition metals are our type 2. There's our predictable charges, okay? Here are some of the varying charges for some of the transition metals. Don't worry about memorizing these. You will be able to figure the charge out from the formula, so I don't expect you to know chromium can form either a 2 or a 3+. Don't worry about that. What I do want you to see though is, do you see how this is a chromium with a 2+? The way that they write that name, they don't just write chromium. They write chromium, and in Roman numerals, they put a 2. Okay, the 2 is the extra piece of information that lets you know that we're dealing with chromium with a 2+ charge. Chromium with a 3+ charge is called chromium 3. If we go down to tin here, tin with a 2+ charge is tin Roman numeral 2. Tin with a 4+ charge is tin Roman numeral 4. Okay, so you have to add a Roman numeral to let the reader know which charge you're dealing with. All right, so the simple one, it's called binary ionic compounds. Binary meaning it contains only 2 different elements. So this is just a metal and a non-metal. We're not dealing with any sort of polyatomic ion here, all right? Just like Na and Cl. We can use that as our example. We've got Na and Cl. So when we're going to name this, it's a metal, it's a type 1 because it has a predictable charge. We're going to say the name of the cation, and that's just a fancy way of saying metal. So we're going to name the metal, sodium. We're going to take the base name of the anion. So instead of using chlorine, we'll use chlor, and we're going to add an IDE to the end of it. So it becomes chloride, sodium chloride. We don't call it sodium chlorine. We call it sodium chloride, okay? So the IDE is letting you know that you're talking about the element. And that's it for that one. So here, sodium chloride. What if we have, let's do another one. Ca3N2. This thing here is calcium. That's the metal. It's got a predictable charge. And then we list the non-metal. We take the base though. We don't use nitrogen, we use nitr, and we ide it, nitride. Nitride. Calcium nitride. Nothing too revolutionary, right? We just are really iding the second guy. What are the bases that we pull off of the nonmetals? Those are these here. So fluorine becomes fluor or fluoride. Chlorine becomes chloride, bromine becomes bromide. Oxygen does not become oxygenide, it's oxide. We truncate that one pretty extreme. We just take the O and the X, okay? Sulfur becomes sulfide, nitrogen becomes nitride. Good with that, with those names? Okay, I want you to name a couple. And I feel like this, you know, the naming thing, it's kind of simple when you're doing it step by step, right? It gets trickier when they're all jumbled together and you're like, where am I? What am I doing? And what section are we in? So we'll do them step by step. And then later on, I'm going to just throw a bunch of things together and you're going to go to town on it. The lab is really, really good this week. I'm practicing all this naming stuff. We may on Thursday actually pull the lab out and do some of that together. Okay, Na2S, RBF, ALP, MgO. All right, go ahead and name these for me. You have the formula. I want you to tell me what the name is. Give me 1 more minute. So all of these are, I mean, the first thing you always want to do is check and make sure, is this a metal and a non-metal? Okay, because if for some reason I had thrown something in like this, CO, that is not a metal and a non-metal. It doesn't follow the system that we're using, but they are all that. So we named the metal first, sodium. And then we eyed the second guy, sodium sulfide. This guy here, rubidium fluoride. Eyed. Potassium phosphide. And last but not least, magnesium oxide. Let's look at this sodium sulfide for a second. I want to just make sure we're really taking a look at those endings. Okay, so sulfide, what is sulfide? Sulfide is talking about sulfur. Okay. What is sulfate? Sulfate is a polyatomic ion, SO4, with a 2- charge. What is sulfite? Sulfite is a polyatomic ion, SO3, 2-. So it is important to make sure, that's an R, that you're looking at your endings and you know what you're talking about. Okay, so if I say sodium sulfide, I'm talking about sodium with sulfur. If I say sodium sulfate, I'm talking about something with the sulfate ion. If I'm talking about sodium sulfide, I'm talking about the sulfite ion. So getting those little details down makes a huge difference. Just a couple letters totally changes what the formula is. So what happens when we have a varying charge? The charge needs to be specified for the metal that we're looking at. You're going to include that with a Roman numeral. It's going to follow the same system though, as far as like the name of the metal. You're going to add though a Roman numeral to tell me what the charge is of that metal, and then you'll take the anion and you'll eyed it. So the same, just have to add the Roman numeral. So when looking at this, like if we're dealing with copper with a 1+ charge, it's copper 1. If we're dealing with copper with a 2+ charge, it's copper 2. Okay. How do you get that charge? Well, you have to work backwards from what you do know to get what you don't know. So let's look at FeCl3. FeCl3. This is a metal with an unpredictable charge because it's sitting in the transition area with a nonmetal. So what I like to do with these is I kind of write a skeletal name for it. I know that this is iron, so I'm going to write iron. I know iron has an unpredictable charge, so I'm just going to put a parenthesis in there to hold the place. And then I'm going to write whatever the second thing is, that's chlorine, so I'm going to chloride that. Chloride. So this is a type of iron chloride. Well, what is the charge on iron? You go from what you do know to get what you don't know. We know for a fact that this whole thing always has to equal a 0 charge, right? So I'm going to cut this thing in half and separate where my metal side from my non-metal side is. Or this is my positive charge side and this is my negative charge side, right? Those two things have to equal each other. Well, what is chlorine's charge always? It's always a 1-. Chlorine always has a 1- charge. How many of them are there? There's 3 of them. So what is the overall negative charge here? It's a 3- charge. So what does iron have to be to balance that out? Iron has to be a 3+ to balance out the 3-. So this becomes iron 3 chloride. You always will know what the charge is on the nonmetal, and you can inadvertently find the charge of the metal. What if instead of FeCl3, this was FeCl2? Okay, we'd go through the same process. This is also an iron chloride. Cut it in half. You know that it has to equal 0. Chlorine is a 1- charge, and there's 2 of them. So this is a 2- charge. So that means the iron has to be a 2+ charge. This is iron 2 chloride versus iron 3 chloride. They will have different properties to them. Just finish it up. What if we did it as FeCl? And this is also an iron chloride. And this one, chlorine, so the whole thing has to equal 0. Chlorine has a -1 charge, and there's only 1 of them, so this has to be a 1+ charge. So this is iron 1 chloride. So you're never going to just have to like make the charge up out of thin air for those transition metals. You'll always be able to read it off the formula. So yeah, we've got iron 3 chloride. Let's do some practice with those though before we go into polyatomics. So I want to do, we'll do 2 together. So let's do CuO2, and then we're going to do Cu2O. So both of these things contain copper and oxygen, but they have different formulas and they'll have different properties. They're both copper oxides. So I'm just going to write for each of these copper, put my parenthesis there, and then put oxide. Do it down here as well, copper, oxide. So now we've got to do the work of figuring out what the charge is on those coppers. I am going to cut these things in half. I know that they have to equal 0. So for this first one, oxygen always has a 2- charge. That's never going to change. That is what oxygen is. And there's 2 of them, so I need to multiply it by 2. So this has an overall 4- charge. So copper has to be 4+, or this becomes copper 4 oxide. Okay, this next one down here is a little bit trickier. How many oxygens do I have? I only have 1, and oxygen always has a 2- charge, right? So this is an overall 2- charge. That means that this side over here has to be a 2+ charge. But how many coppers do I have? I actually have 2 coppers. So that means that this 2+ is going to be distributed, or it's going to be broken up amongst each of those coppers. So 1 goes to one copper, 1 goes to the other copper. So each copper has a 1+ charge. There are 2 of them, bringing the 2+ total charge, but each one has an individual charge of 1+. So this formula is actually copper 1 oxide. If you're like, well, but it's 2+, so it should be copper 2+. Well, but it's distributed over 2 coppers. And we can actually go through, let's write copper 2 oxide. One thing you can do is go back and check and make sure that you get the same formula. So let's say you're going to be stubborn here and you're saying, no, I don't think that this is copper 1. I think this is copper 2. Well, let's write it out. Cu with a 2+ charge, oxygen with a 2- flip-flop. I'll get Cu2O2. What does that reduce down to? CuO. Is that this? No, it isn't. Let's do the one that I'm telling you is correct. Cu with a plus charge, O with a 2 minus charge, flip-flop, what do I get? Cu2O. Is that the same? It is. So this one is the correct one. So if you ever have multiples of the metal, you've got to divide it by however many you have. That's, I think, one of the trickiest things for people to understand when they're doing these ionic namings. Okay, let's take a 10-minute break because we're going to lecture, maybe not the whole time, but we're going to lecture for at least another hour. So let's take a 10-minute break. I'll see you guys at 11:05 and we'll do some practice with this stuff when we get back. Hello, hello. Bring you all back. We are going to do some practice with those varying charges. So let me share my screen with you again. All right, so I'm going to start listing out. I'll give you like 5 of them. I want you to work through naming them. Okay. Hmm. Sorry, give me just a second here. All right. So you've got NIN, ZN3P2, CR2, OPTS2, and ZRCL. So I want you to name all of those guys. Give you at least 5 minutes for it. And then we will go over them. Again, all this stuff, this naming stuff, I would say is like the most important thing that y'all can do this semester. So make sure if you're having questions, you're not sure where things are coming from, ask. And if you want, you can just put it in the chat, and you can even just send it to me privately. And I won't use your name, but I can go over that specific thing. So while you're working through these, if a question pops up, throw it in the chat.
Mrs. Henderson, I have a question.
Give you just another minute, 45 seconds. Okay. So first one here, NiN. This is not 9-inch nails. This is nickel 3 nitride. Let's talk about how we got that. So we know that this is a metal with an unpredictable charge, nickel. I'm gonna write that. I'm going to put the space there, and then this is nitride. The IDE is talking about the element. So we don't have like any polyatomic ion here. It's just nitrogen. I'm going to cut it in half. The nitrogen has a 3- charge, and there's only one of them. Okay, the nickel has a 3+ to balance out the 3-. 1, 2, 3. So we get nickel 3 nitride. The second one here, this is zinc, Zn, not a 2. Sorry, my handwriting is horrible. This actually has a predictable charge. I threw that one in there just to test you guys. So zinc is always a 2+ charge. So you might have gone through and like calculated, oh, well, it's a 2+ charge, but zinc, didn't we say that that was a predictable? So we're just going to go with zinc phosphide for this one. Aluminum is a 3+, zinc is a 2+, silver is a 1+. Don't need the Roman numeral. Okay, this next one, chromium. That does have an unpredictable charge. I'm going to put a Roman numeral, and this thing here is oxide. Okay, let's cut this thing in half, figure out what we've got. 2- on this side, there's only one of them, so it's a total 2- charge. So this has to be a total of a 2+ charge. But tricky, there are 2 of them, so I need to take this number and divide it out by 2. So this is going to be chromium 1 oxide. Each chromium brings a 1+ charge. There are 2 of them to give us the total 2+ charge to balance the oxygen. This thing here, this is platinum. Unpredictable charge, and then that's sulfur, or we go with sulfide. And the IDE letting us know it's just sulfur. We're going to cut it in half. Sulfur always has a 2- charge. In this case, though, there are 2 of them, so we need to multiply it by 2. So there's a 4- charge happening on this side. There's a 4+ happening on this side. How many platinums are there? There's just 1 platinum, so it eats up that whole charge. So platinum 4 sulfide. This last thing, zirconium. It always sounds so like futuristic to me, zirconium. All right, zirconium, and then we've got chlorine, which is chloride. Figure out the charge. Chlorine is a -1. There's only one of them, so zirconium in this is a 1+. Zirconium 1 chloride. Sometimes students will ask me, oh, can I leave the 1 off? Is it just assumed? No, you do have to put the 1 in the Roman numeral, okay? So with the subscripts, like here, you know, like nickel, there's 1 nickel and 1 nitrogen. Those we can say that there's just an assumed 1. We can't assume a 1 charge. So someone had told me, hey, can you go over the endings, the IDE, ATE, ITE stuff? We're going to do that right now. We're talking about polyatomic ions a little bit more. So naming compounds containing polyatomic ions. So if it has a polyatomic ion in it, you have to name it as such. It's pretty easy. if there's a polyatomic ion, you don't change the polyatomic ion. You don't like truncate it. You don't IDE it. You don't do anything. If it's sulfate, you just write the word sulfate. So let's look at this thing here. We've got potassium and nitrate. Now, you've got to get in the habit of looking at this and saying, oh, bam, there's a polyatomic ion. How are you going to do that? Practice. Memorizing your polyatomic ions helps. Another thing, anytime you get to a place where there's like more than two things, it's a polyatomic ion. Okay, so if you're like, I'm trying to flip-flop, name this thing and it's not working, there's too many things, check your polyatomic ion list. So the name for this is real straightforward. That's potassium, that's nitrate, potassium nitrate. I don't ADE it, I don't ITE it, whatever. I just keep it as is, ATE. What happens if we have a situation where we have a type 2 or one that has a varying charge? We have to specify that with the metal. So here we've got iron and it's combined with something called hydroxide. This is one of the few polyatomic ions that ends in IDE. And I know that can sometimes throw people off. They think, oh, IDE always talks about an element, not for hydroxide. Hydroxide is talking about hydrogen and oxygen together, OH with a minus charge. So when you work this out, this is iron, but it's specifically iron 2 hydroxide. Hydroxide, if you look at your periodic, your polyatomic ion sheet, is OH with a -1 charge. There's 2 of them, that's 2 minus, that has to be 2 plus to balance it out. It's not more complicated than what we were doing before. It's just, you need to be able to identify that there's a polyatomic ion, I think is the main thing where people are like, oh, what is this? If you get to a place when you're naming, you're like, oh, how do I do this? Check your polyatomic ions, like every time. Here's one where ammonium is acting as the metal and nitrate is acting as the non-metal. If I was to name those, you just smush the polyatomic ions names together. Okay, you don't like have to do anything else. So I would just call this ammonium nitrate. Let me leave it at that. So with the polyatomic ions, you may start to see that there is a pattern specifically based off of the number of oxygens. So a lot of compounds contain what are called oxyanions. These are polyatomic ions that contain oxygens. And they usually are named in a series. And that series is based off of the number of oxygens. So when looking at the nitrate, quote unquote, nitrate series, nitrate has 3 oxygens. The ite will always have 1 oxygen less than the 8. That doesn't mean that nitrate, or it doesn't mean rather that ATE always has 3 oxygens. In this case, it has 3 oxygens. Over here, this 8 for sulfate has 4 oxygens. It just is in relationship to the other oxygens. So nitrate has 3 oxygens. Nitrite, you'll strip an oxygen, you keep the charge the same. It's NO2 minus. Sulfate, ATE is 4 oxygens with a 2 minus. Sulfite will be 3 oxygens with a 2 minus. Strip an oxygen. So if you know your 8s, you can figure out your ites really easy. Just cut the oxygen off. The series actually expands outside of 8 and ite. You can have this sort of like 4 series. So we've got perchlorate, or rather chlorate. Chlorate is ClO3 minus. Chlorite is ClO2 minus. Those we know. Ites are 1 oxygen less than 8. What if we went into, what if we cut another oxygen off? So we took our chlorite and we stripped another oxygen. We get something called hypochlorite. Hypo being under, hypoglycemic. Let's say we're at chlorate and we want to add an oxygen in that series. It becomes perchlorate. So we keep the ATE and we put the per in front of it. Same thing if we look over here, we've got bromate, bromite, hypobromite. If we have more than bromate, we have perbromate. So let's do some naming with with that stuff. We're going to go in both directions. We'll start with the formula, and I want you to give me the name, and then we'll do name to formula. So FeCO3 no, do something different. I want to give you guys a couple that are in a series though. FeCO3, COSO4, COSO4, 2. Actually, I'm going to make that SO3 too. Sorry, guys. SO3. Come on. 2. And then I'm going to give you COS2. And then let's do V2O3. CU 3PO4. Okay. So I want you to name all of these. Give you guys 5 minutes. Give you all 30 seconds, finish up where you're working at. All right, so naming these things. Here we have a metal with a polyatomic ion. It's also a metal that has an unpredictable charge. So this is going to be iron with some sort of Roman numeral, and then this clump over here is carbonate. I need to figure out the charge on the iron. Well, carbonate always has a 2- charge. There's only one of them. Yes, I know there's 3 oxygens, but remember this is a packet with a 2- charge. So the whole packet has a 2- charge. So iron will have a 2+. This will be iron 2 carbonate. I gave this sequence here so we can sort of differentiate the names, ATEs, ITEs. So this is cobalt with a polyatomic ion called sulfate. Cobalt, put a Roman numeral in there, and then sulfate, ATE, 4 oxygens. Cut it in half. This has a 2- charge, so this will have a 2+. So this is cobalt 2. This thing here, this is cobalt combined with something called sulfite, ITE. Slightly different than sulfate, 4, 3. Okay, I'm gonna cut that in half. Sulfite also has a 2- charge, but there's 2 of them, 2- C times 2. So an overall 4- charge. So cobalt here is a 4+. This wasn't a sulfate, this was a sulfite. This is cobalt sulfide. IDE, talking about the element. Cut it in half, 2- for the sulfur charge, but there's 2 of them, so times 2 for an overall 4-, which makes this a 4+. It's all just 1 cobalt, so this is also a cobalt 4, but this is cobalt 4 sulfite. This is cobalt 4 sulfide. Okay, looking at these over here. I've got what, vanadium, vanadium. Vanadium, some sort of Roman numeral, oxide. Okay, so we need to figure out our charge on that. Oxygen has a 2- charge. There's 3 of them though for an overall 6- charge. That means that this has to be a 6+ charge, but there are 2 of them. So I have to divide it up, or it's going to be a 3- for each vanadium. So this should be vanadium 3 oxide. This last one here, copper, that's phosphate, ATE, talking about the polyatomic ion. And cut it in half. Phosphate always has a 3- charge. That means cobalt has to have a 3+ charge, but there are 3 of them, so divide it up amongst 3. So each one has a 1, copper 1, phosphate. We have named them all. Okay, questions? You gotta ask me, otherwise I would assume that you are like good to go in this direction. No questions? Us expert neighbors? No. At least do you understand the concept, right? Obviously practice will need to happen in your own little worlds, but the concept you get. Can you explain the ending of the sulf? Yes. So when we're looking at these different things, right? We see sulf is in each of them, but they're talking about different like materials. So sulfate, ATE, is talking about SO4, 2 minus. Sulfite is talking about SO3, 2 minus. Sulfide is talking just about sulfur. How do you know this? Well, get in the habit of seeing IDE as being most of the time correlated with the element. ITE and ATE are polyatomic ions. Just check your polyatomic ion list. Does that give clarity? Okay, awesome. So why don't we go the other direction? Because sometimes you're given the name and you have to write a formula. So I'm going to mix this with it's going to be type 1 and type 2 and polyatomics and not polyatomics. It'll be all sorts of different things, okay? We're just going to do it. So let's go with, so I'll give you the formula, you name them for me. No, I'll give you the name and you give me the formula. Okay, cobalt, 2, phosphate, calcium carbonate, rubidium, fluoride, aluminum, sulfite, titanium, 3, nitrate. I'll give you 2 more. Oh, come on, Candace. You can come up with something. Iron. 1 hydroxide. And silver acetate. Okay, so these are the names. I want you to write the correct formulas. I'll give you another 5 minutes for those. Just another 30 seconds. And we'll come back together as class. Okay, so here we're trying to come up with a formula from the name. So you've got to know what you're looking at. Cobalt is a metal with an unpredictable charge, but it's written for you here. So we're going to use the 2+ because it told you it's the 2+. Phosphate is a polyatomic ion, PO4, with a 3- charge. We flip-flop cobalt. Cobalt gets the 3. Phosphate gets the 2. What sometimes happens is people will see this and they will think that it means they have 2 cobalts. Okay, I'm going to write it in red over here, what is not happening. So they'll go, oh, well, cobalt, I've got 2 of them because it's cobalt 2, and then phosphate, whatever. I'm just going to like write it in. I don't know. No, you've got to make sure that this is getting put at the charges position, and then from there you flip-flop. That makes sense? Yes, no, maybe so. Good, James is good, okay. Calcium carbonate, metal and a non-metal, metal with a predictable charge. So calcium, if you're like, what's the charge on it? Remember it's in column 2, so it has a 2+. Carbonate, CO3, has a 2- charge. Flip-flop, the 2 and the 2 are just going to reduce down anyway, so I'm just going to write it out as CaCO3. Rubidium fluoride, rubidium Rb has a 1+ charge. Fluoride is talking about fluorine, which is, sorry, just an F, with a minus. Flip-flop, it should be RbF. Okay, aluminum sulfite. So this is where you got to start asking yourself, am I talking about a polyatomic ion? Am I talking about the element? Which polyatomic ion am I talking about? So we've got aluminum, which is a 3+, sulfite, which is SO4. No, it's not. It's SO3 with a 2- charge. Flip-flop, I'll have 2 aluminums for every 3 sulfate. So it's SO3, 3. Again, sometimes the double 3 freaks people out. Don't get freaked out. Titanium nitrate, specifically titanium 3 nitrate. So I've got the titanium Ti. It's got a 3+ charge. That isn't telling me how many titaniums, it's telling me the charge on it. Nitrate is NO3 with a -1 charge. Flip-flop, I'll have 1 titanium and 3 nitrates. Iron 1 hydroxide. That means I have iron with a 1+ charge. I've got hydroxide, which is OH-. Okay, that's one of the polyatomic ions that does end in IDE. It's just how it is. So we're going to flip-flop. Fe, OH, 1-to-1. We don't need any like parentheses or anything like that. All right, the last one, silver acetate. Silver acetate, we've got silver, Ag, which always forms a + charge. because that's just one of the ones that I've told you has a predictable charge. Acetate, C2H3O2 has, oop, put that 2 down here, has a minus charge. There will flip-flop, and we should just get Ag C2H3O2. No need for parentheses because there's only one acetate. So usually people have like a more preferred way of doing these. I find this way for me easier than the other way, like going from the name to the formula. Some people like prefer going from the formula to the name. So yeah, that is all the ionic stuff. All right. I do want to get to molecular stuff before we leave today, just so you have that in your toolkit when you're doing homework and stuff. The molecular is so much easier. It's like 3 slides long. Yeah, I think it's literally 3 slides long. Okay, so this should feel much easier. Well, first you have to identify it's molecular. So what tells you that it's molecular? It's nonmetals. It's a bunch of nonmetals smushed together. So how we do this is we're going to take the name of the first element and we're going to give it some sort of prefix to let you know how many of them you have. So if you've got, 5 of them, it's pent. If you have 2 of them, it's di. The prefixes are on the next page. So you'll name the first element with a prefix. Then you'll take the base name of the second element, you IDE it, just like we did with the metal nonmetals, but we add a prefix. And that lets us know how many of them there are. Here are the prefixes. 1 is mono, 2 is di, 3 is tri, 4 is tetra, like tetrahedral, 5 is penta, like a pentagram, hexa is 6, hepta is 7, octa is 8, nona is 9, deca is 10. You got to know the prefixes or, at least have access to them. When we're dealing with molecular stuff, there is no charge differential. There's no like positive and negative charge because they're all nonmetals. So everything is a negative charge and we're not transferring electrons, we're sharing electrons. So there's no need to flip-flop charges. We don't do that for this. All we do is you look at how many there are and you give it a prefix and that's it. This one gives us, there's one exception where you can drop a prefix. If you happen to have mono on the first thing, just the first one, you can drop it, okay? So this is CO2. If we were to follow the system, it would be monocarbon dioxide. We can drop the mono because anytime there's one on the first, you can drop it. You can't drop mono on the second though. So I'll draw this guy here, CO. This would be what, monocarbon monoxide. We don't call that monocarbon monoxide though. What do we call it? Carbon monoxide, because we can drop the mono on the first. We can't drop the mono on the second. And you cannot drop di, tri, tetra, any of those on the first. The only thing you ever drop is if you have one on the first thing in your formula. That's the only time. Other than that, always include it. Sometimes there's things with the vowels, like when the prefix ends with a vowel and the base name starts with a vowel, the first vowel is sometimes dropped, but then of course, obviously it's sometimes not dropped just to make it confusing. So vowel that's dropped, monoxide, but dioxide, the I stays, and triiodide, you actually keep both of those I's. I am not going to test you on spelling because I have no capacity to spell anything, especially now that I have my kids. It's like just that information is gone. So I won't give you like an option where it says triiodide with 1 I and triiodide with 2 I's. Okay, that won't be the case. So let's do a couple of these. They're super easy, I feel like, compared to the last stuff. So this thing right here, C2, S5. All right, if I'm going to name this thing, I just look at how many I have and I put it as a prefix. You don't put this as the prefix on the other guy or this is the we don't flip-flop. It stays true to whatever it is, okay? So if it's carbon and there's 2 of them, that's going to be dicarbon. How many sulfurs do I have? 5. Pentasulfide. Dicarbon pentasulfide. These ones kind of make you sound smart. Like if you can read them, you know. Let's look at N3O6. You don't reduce too. That's another thing with molecular, don't reduce. So this would not get reduced down to NO3. Okay, that doesn't happen here. We keep it true to however many it has. So we've got 3 nitrogens. That would be trinitrogen. 6 hexa, I think it's hexoxide. I actually don't 100% know. It could be hexoxide. I think it's HEXOXIDE. I have trouble with which vowels get dropped and don't. That's pretty easy, right? That's it. Now you can name moleculars. You're done. You're done. So like, let's go the other direction. Let's say I give you disilicon octafluoride. And I want you to write a formula for that. Okay, so the prefix tells you how many you have. Silicon is Si, and I have 2 of them. Fluorine, fluoride is talking about fluorine, and I have 8 of them, and we're done. Isn't that refreshing? Isn't that nice compared to all the other stuff? It's not too troublesome. We're gonna write this next thing in red because we don't want to do this. Okay, don't do. Get something like this, Al2O3. Every time I get people who go, oh, that's dialuminum trioxide. I'm thinking, oh, look at how clever and nifty I am, right? Why is this wrong? Because this is ionic. We do not use prefixes anywhere near something that is ionic, okay? If it has a metal in it, if it is ionic, I do not want to see you write a prefix. Is this going to be an option in your multiple choice if this was something you had to name? Oh, for sure, because this is an easy one that people like to pick at. They see that, they go, oh yeah, there's 2 aluminums and 3 oxygens, dialuminum trioxide. Don't do it, okay? Don't fall for it. If it's a metal and a non-metal, work on the flip-flop charge thing. If it's 2 non-metals, that's when you get to go kind of the easy route and use just prefixes. So it gets much more troublesome when everything gets jumbled together. The last thing I want to talk about is acids, and then that will have been the whole lecture, and then we're going to work on the lab on Thursday together. We'll do more practice. We'll work on the lab on Thursday, and then we'll probably lecture a little bit ahead so we don't get so smushed, because next week we have to do 2 chapters. So I'm going to stretch that out a little bit. So the last naming thing, okay, and then this flow chart here, which again, I think is really lovely if you can get this printed out, which kind of gives you everything on how to name stuff. So we've got, you know, if we're ionic, if we're a type 1 or a type 2, how do we name? If we're molecular, use our prefixes. Now we're going to talk about this thing called acids. Hold on 1 second. Someone asked, should we do the lab before or wait until class? You don't have to do the lab before. If you want to look at the lab, if you want to start looking at it, that's always useful, because then you can ask me specific questions about things that you have, but you don't have to, no. All right, so this last section is acids. So how do we determine if it's an acid? For right now, our simplified definition of an acid is going to be that it contains an H. So you have to be able to identify it. So acids are molecular compounds that form ions when dissolved in water, and they are composed of hydrogen, and the hydrogen is usually written first. with one or more nonmetal as their second position. So the polyatomic ion, this OH minus, is not an acid. Okay, we don't classify that as an acid. The H isn't written in the front. Something like this, HCl, this is a great example of an acid. Hydrogen written first with some sort of nonmetal. We can classify acids into two groups. They can be either binary acids. This is an example of a binary acid. Binary, like a binary star system, 2 stars, it's just 2 things. It's hydrogen with one other thing, okay? So a binary acid is hydrogen with a nonmetal. An oxyacid is hydrogen combined with some sort of polyatomic ion. You want to be able to differentiate those. So like HNO3. This would be an example of an oxyacid. It contains hydrogen mixed with a polyatomic ion. We name those slightly differently, so you want to be able to define them. So if the formula is binary, this is the way you name it. You say the word hydro. You take the base name of the nonmetal and you ick it. And then you add the word acid. So HCl, is this binary? Yes, made of 2 things. We're going to follow this system right here. That means the first word I write is hydro. Then I take the base name of the metal, or rather the base name of the nonmetal, and this is chlorine. So I take chlor and I ick it, chloric. And then I write the word acid. Hydrochloric acid. Have you heard of hydrochloric acid? Probably, it's pretty common acid. The hydro and the nonmetal get smooshed together. So smoosh those. Hydrochloric acid, this one here, HBr, this is hydrobromic acid. Of course, there has to be one that gives us trouble. So for this guy here, we don't call this hydrosulfic acid. This is hydrosulfuric acid. It doesn't truncate it. Just one of the ones that doesn't follow the rule. What happens if it's combined with an oxyacid? So like HNO3, this is an acid that has nitrate, right? The nitrate ion. H2SO3, this has the sulfate ion. H2SO4, this has the sulfite ion. When naming these, we don't say the word hydro in the front. We just say the base name of the polyatomic ion or the oxyanion ion, and we change ite to us, O-U-S. We change ate to ick, and then we add the word acid. So I ate something icky. That's one way to remember it. I'm going to write 2 different ones here. So let's say for this guy, we have HNO2. And for this one, we have HNO3. This is hydrogen mixed with nitrite. Ites become us. So this is nitrous acid. This is hydrogen mixed with nitrate. Ates become ick. So this is nitric acid. We don't put the hydro. Okay, people like want to have because they did it for the other one, they want to add the hydro here. You don't, just hydro for binary. And that's it for the acid. So here are some examples of, the ite becoming us, the ate becoming ick. And then all of that summed into one giant chart. So everything we went over sort of culminates right here. Wow, that was awesome that we got through all that. Great. So we will call it for today. We are going to totally do more practice on this. So don't stress if you kind of get the concept, but you still have detailed questions. We're going to practice some more on Thursday. Otherwise, enjoy the rest of your day. If you have any general questions, throw them out. Personal questions, just hold on and I'll bring you in one at a time. Thanks so much for your patience today, and I will see you next time.
Thank you.